Welcome back to General Structures 2 and Lateral Forces, lesson number 3, example number 2, and I believe this is part 3. And we left off where we just figured out what FBC was. And we found out that FBC equals, what, 3.75, and I said that was a negative. So we assumed it was going down, correct? Yes, so instead FBC is going to be going up. All right. And that's FBCX right here. FBCX, FBCY. And anyways, yes, and that's kind of confusing because it's about an FAC down there as well. All right, now what we need to do is figure out what FBCX is, and we can do that through similar triangles. And that's actually, if you look into the, I looked into the study guide, and that's how they figured out without getting all these angles and whatnot, is they use similar triangles. And we know that this distance right here equals 5 foot, and we know that that distance right there equals 10 foot, and we know that this distance right here to that point equals 13 foot 4 minus 10 foot, so that's 3 foot 4 inches. So if we think about it, we have, I'll come up here real quick, we have a triangle that looks like this, and this is 5 foot, and this is 3 foot 4 inches. Alright, and then we also know, when we're thinking about similar triangles, is we know that FBCY. So we know FBCY equals .75. That's going up because we assumed it, or you could say, let's say compression, so we don't get confused. And then we need to figure out what is this, because remember, these are similar triangles, and we need to figure out, and this is the fourth of BC in the x direction. Alright, so we can set up an equation to figure that out. And I've always remember similar triangles is I will just set the sides equal to each other. So for instance, go 5 foot over 3 foot 4, so 3.33 foot equals, and I put the same side on the opposite one, so this would be 3.75 over x, or FBC x, or whatever your unknown is right there. And then you solve for that, and we need to take that over there, so we could actually have done this differently to make it a little bit more. Actually, I'm gonna go ahead and do that right now. If you put FBC on top, it's the math looks easier and it's less confusing, and that's why I want to show it to you. So let's start with FBCX. Okay, so we have FBCX over 3.75 foot equals the same one on the bottom, so that's 5 foot on the bottom, and the same as FBCX on top, 3.33 foot. And then you can solve for that, and that's a little bit easier to see the math of how to go about that. You take this and you multiply, actually you take this and multiply it by 3.75, and you get 3.33 divided by 5 times 3.75 equals 2.5. So FBCX equals 2.5 kips in compression. Again, because if one's in compression, both of them have to be in compression, so they will go into the joint. And then we have, where are we at now? We need to figure out what FBC is as opposed to the components. And an easy way to do that is to use Pythagorean theorem. And I'm not going to write it out. I'm simply going to tell you what I'm doing. I'm going to say 3.75 squared plus 2.5 squared. I hit enter, and then I take the square root of that answer. So I take 3.75 squared plus 2.5 squared, and that equals 20.3, and then I take that to the square root of that, or to the 0.5, and I get 4.51, let's say, or 4.50, kind of depends how you round. I will go ahead and say 4.51. FBC equals 4.51. And remember, that is in compression, and that was the Pythagorean theorem that I did. Remember, you have this right here, you have this right here, and you're looking for this right here, and therefore that side squared times this side squared, and take the square root of that, and you get this side squared. A squared plus b squared equals c squared, in other words. Alright, so we have FBC. Wow, this is incredibly messy. So what I'm going to do is I'm going to set it up here. Let's make sure we have FBC correct. Let's go back into the study guide and check on it. What is FBC? Which is also known as F23 in the study guide. Equals a negative 4.5 kips in compression. We said 4.51, good enough. Compression, alright, we're good. So we'll just go ahead and write it up here, and I'll leave it up here. FBC equals 4.51 or 50 kips. Kinda, I rounded up because I got a 4.506, and that's not something you should worry about at this point. Structural engineering, nothing's perfect. You have you'll end up having a lot of different factors when you go into this, and then once again, this is depending on what type of code you're designing for. But if you're designing for ASD, which is allowable stress design, for instance, you will take a certain percentage of the allowable yield stress for your bending and shear. Usually use like a 0.55 or a 0.6 of your shear stress, or of your bending stress. So you'll see this type of writing, and I might be confusing. If I'm confusing you, don't worry about it. You'll see this 0.6 Fy equals Fb. So this is your, what I like to call service load. So it depends what you're doing. When you're doing ASD, you factor down your allowable to get your allowable bending. And if you're doing LRFD, then you will take, it's going to be less. It'll be, let's say, 0.9 for your allowable, or something like that. And then over here, you'll actually take this, and this is assuming that this is all, well, you'll say you'll have 0.25 is your dead load, and your live load equals 2.00. So you have to actually multiply these by, say, now remember, I'm just guessing here, 1.6, let's say, and this is going to be 2.33, and you have to multiply every single one of your load factors compared to what load combination it is, and it gets confusing. So I'm not going to get into it right now. This is your service load. Service load is just when you're, or some people call it the nominal load. So that right there is our answer for FBC. I'm going to move on because I think I'm just confusing. Alright, now we cut it right here. Now we need to find out what, I think it was 3,4, which is this member right here, which is CD. Whoa, I got off track. CD. So this member, right, close enough, right there. So we want to cut it right here. Excuse me. And let's take a look at what we got here. We have A coming up, and we'll say a dot 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 to D. B is coming down like so to C, and we're coming straight over. So we have A, C, B, here's D, and then we have this member coming over, dot 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 dot. This is dash lines, is what I'm saying. It equals the cut member, and let's put this right here. Would be good enough. Good enough for government work. All right, E. There we go. And there's our cut. Our cut was right here. So the easy way to go about this is we need to figure out what C is, and therefore how do we go about doing that? Well, we need to isolate it. And how do we isolate it? Well, remember we're going to assume all these are positive. So you have FCD, you have FCE, and you have FBD. And real quick, hopefully by now you know the best way to isolate when you have a lot of different forces is to go ahead and do the sum of moments about a point. And hopefully you can come up and you will know before I tell you right now which point you should rotate this about to isolate, to get rid of your unknowns, I guess, your unknowns. And there's a certain thing you want to do. You want to get rid of this one, and you want to get rid of this one, because that will leave you FCD, or also F34 is what we're looking for. This is F34. In the example, I just renamed it FCD. And hopefully you know that, hey, if I make these two congruent, I can get rid of those the moment congruent force is 0. So hopefully you can say, oh yeah, if I do it about A, those both forces are going through A, and FCD is not, and therefore FCD will induce a moment, but the other two will not, and we will be good. So we want to do it about point A equals 0. And really what you need to do is come in and put the rest of your forces, and I forgot to do that in one of the videos, and I had to go back and correct myself. So we have 5 kips, 3 kips. This is obviously not going to induce a moment. There's your 5 kips. Alright, and I believe we're done. So because we don't, since we cut it right there, we don't want to include that 5 kips up here. That is not part of our free body diagram we have here. Alright, now we want to go from left to right, and let's go ahead and figure out what this is. We have 5 kips, and that is at what? 10 foot parallel. Yeah, that's right, 10 foot. And then we have, so once again, this is one of those things where you could figure it out, where do you want to put FCD? And I don't believe it matters at all where you want to put it, but let's put it up here. We'll put the, actually let's go ahead and put it down here. So if you have FCD, we'll assume it starts at this point. It's that infinitesimally small point. That's your FCD. Let's go ahead and switch colors here so you can tell what I'm trying to do. And there is going to be that. So this is your FCDY and then FCDX. Alright, so FCD, shoot. Let me put FCDX down here. We'll put FCDX down here so I don't confuse. FCDX, FCDY. And I put that down here so it doesn't confuse you, to know, hey, that FCDX is congruent. So you're going to get a 0 for the moment induced by this FCDX since it's going through point A. But FCDY is going to be 13 foot 4 away. So let's go ahead and enter that into the equation here. And that's going to induce a negative moment since we defined positive is going that way. So we have our FCDY times 13.33 repeating foot. And that's all we have. So what we need to do is solve for FCDY. And I forgot to make it a negative. This will be a negative FCDY. So 5 times 10 equals 50 divided by 13.33. Let's add a couple more 3's on there for good measure. And we get 3.75. Remember, I changed this to a negative because it's going to make that type of induced moment, and that's going to be negative because we define positive moment as going that way. Alright, so 3.75, and it's positive, so that means it's in tension. And we're out of time, so I'll see you on the next video.